Okay, there you are. Let's do it. So let's give you the review first, then we get to the what is calculus about. So we are going to review the notion of the functions. As I talk about it, when we're done this afternoon, I will get the recording from the Zoom. So I post this recording, then I make a PDF file of my lecture notes, whatever we did, then I post that lecture note for you too. So if you miss anything of the lecture notes, then you will see it. Or if you miss any lecture, then nothing to worry about, okay? So what is going to be the notion of the functions? Anybody wants to tell us what is the function is? Or what you know so far about functions?
Works like a machine. When you input something, something comes out.
Yes, very good. But there is a condition. What is that condition? Yes, that's a very easy way to describe it. A machine. Yeah, that's a good one. A machine. You see, that's it. So let's go with your idea. This is it. So the function is a machine. We call it a function f. But this is a mathematical machine. Mathematical machine will give you mathematical operations. Mathematical operations are going to be what? Addition, subtraction, multiplication, okay, division, raising to the power, taking the square root, the fifth root, sixth root, depends, sine, cosine, etc. So it's a machine, like a cashier, okay? So what we do with this machine is you have to give something to the machine. We give the x, drop the x into this machine, okay? This x is going to be called input. Okay, that would be the input. The machine will do something to the x. You see, we do something to the x. It depends what you already set up into the machine. Okay, you set up with the formula, so the machine would apply that formula to the x. So the machine would give us something out. Something out is going to be called the action of the machine on the x. We call it f of x. But we denote this one by y. And this is going to be our output. Okay, so the input is going to be the x. Okay, you provide the x to the machine, and the output will be y. But there is one condition. The condition is going to be for each x, for each input, the machine would give you only one output. Okay, so if you get x into the machine, the result's going to be just one output. In that case, you are going to have a function. Okay, so a function is going to be a machine, it's a mathematical machine. Mathematical machine can be, or it's going to be a formula involving those mathematical operations. Okay, so officially, let's get it more official definition. Just give you a brief one. Depends, this is calculus, so this is all we need. So we can say that f function. Okay, a function f is going to be, can be a relation. Because you have to tell us what is this machine. Okay, it can be a relation, it can be an equation. Okay, an equation. Or it can be a formula. Okay, a formula. It can be a formula, or it can be a table. Sometimes we denote the function by a table. Okay, a table. Sometimes we use graph. Okay, a graph. Or sometimes we use a chart. It depends on what discipline are you, okay, or a chart. Okay, or a chart that's important, but is that relates, depends on which formula you have, okay, relates each given input, or the x values, input x, okay, input x exactly each given input x, input x to exactly one y, one output, y. Okay, for each x, we get a unique y that satisfies that condition. This y is denoted by f of x. Okay, y is the denoted by f of x, and y equal to the f of x is going to be called the equation of a function. It's called the equation, okay, of the function. Okay, so that would be the equation of the function. Any question? Now the collection of all these x's that going through the machine is going to be called the domain of the function. The collection of all outputs that we're going to get, we're going to call it the range of the function. So the collection of all inputs or x values is called the domain. That's a very important part. Okay, this is going to be the domain, and the collection of the set of all resulted values, which is going to be the same as y values or f of x values. Okay, all resulted values, or let's say output, is going to be called the range of the function. There is, you know, that if you do this one in discrete mathematics, in computer science, we have a domain and the codomain and the range in between. But in calculus, we're just going with this definition. Okay, we agree that this is the way we're going to determine the domain and the range. We are not going to talk about the codomain in this, in this course, if you like. Okay, so the result, the x values is going to be called the domain. If x goes through the machine, x is in the domain of the function. Okay, when x goes through, then you get the result, which is going to be the y's or the f of x. This f of x, you put them together, that would be the range of the function. Okay, any question? Your main job is finding the domain of the function. So let's get some examples of the function. Okay, example of the function. We start with some everyday life examples. I give you one of them, then we ask some you to give us some. Okay, the best one to start with is your calculator. You see, your calculator is a function. It's a very nice function. It's the function. So what we do with your calculator, for example, if you take the x, and then if you click on the square root, say this is going to be a machine. If you click on the square root, so the result would be radical x. Y equal to the radical x. You know that this is the one we call it the square root function. So that would be the square, okay, a square root function. Okay, so it depends on the action that you're going to have. So if you use the square root function, for example, if you put the 4, and if you click on the square root, so the result would be 2, radical 4, which is equal to 2. So this 4 is in the domain of your function, because 4 is going through the, this result. Any question? What would happen if you put the -4 into the machine?
undefined.
Undefined, very good. So let's see, what does it mean? So we get the radical -4. You know that in calculus, we never use complex numbers, remember, never. Because if you want to use calculus, complex numbers, you have to take calculus 1, 2, 3 first, then come back. Okay, if you're measuring physics, we're going to have a course, we call it advanced calculus, or we call it physics, mathematics for physics. Then you will learn those, on those courses. If you are a math major, of course, you are going to see complex functions. So make sure don't use it. We don't use any complex numbers in this course. Okay, radical -5. If you do your calculator, the calculator will give you an error. Okay, so the calculator will give you the error if you use calculator. So this means that's it. This means, or so we can call it, for this function is going to be undefined. You know that if you want to be more precise, it's not a real number, if you like. Okay, this is it. It's not a real number, but it's going to be undefined. So undefined, what does it mean, the undefined? Undefined means -4 is not in the domain of this function, okay? So -4 is not in the domain of the function y equal to the radical x. Okay, so we know that in this course, the square root function would define only for the non-negative numbers. So if you like the domain of this function, okay, so the domain of this function is going to be set of positive numbers only. So we start with a 0 going to the positive infinity. All the domains in this course are going to be denoted by interval notation only, okay, to get this one through. Any question? So your calculator, it depends on the application of your calculator. So if you click on any other format, you're going to have something else if you like. So for example, if you get your x, I'll give you another one here. You see, if you take the x and then if you click on the sine function, so the result would be y equal to the sine x. Okay, so this is going to be the sine function. The sine function. So the calculator is going to be nicely a function. Any question? Okay, so I give you the calculator as an everyday life example. Any suggestion for more everyday life functions? During the day, okay, the way you are going to operate or actions that you're going to have. Can you see any function like calculator that we have in everyday life? Any suggestion? Okay, I'm going to give you some. Where do you get your coffee? You get your coffee from a Starbucks. A Starbucks, we see a number of the nice functions over there. And the menu of a Starbucks is a function. You see the menu of Starbucks. On one side, give you the name of the product, if you like. You see different type of coffee that you have. On the other side, you get the money that you have to pay for it. Okay, so when you go to the cashier of the Starbucks is a function. That's the cashier. So the cashier, you are going to tell them what you have. Okay, white mocha. They click on the white mocha and the machine asks you for what that $4.85 something grandy. So all the cashiers are going to be functions. Okay, for the cashiers, the function is already there. So the Starbucks is going to be a function and that you're going to have, okay, or any cashiers. All the cashiers are functions. If you go to any fast food restaurant, okay, go to the Burger King, etc. As soon as you order, you say they ask for the order, and they click that, they give you the receipt and ask for the money. So all the cashier machines are going to be functions. Okay, you go to the grocery stores, Albertson, Vans, Ralph's. As soon as you arrive, you see the list. They give you a list of the vegetables, oranges, etc. But as soon as you get to the cashier machine is a function. Cashier machine is a function. You see, you get the money, and then they click. They scan the item. When they scan the item, they bring the function. If you scan the chips, the function for the chips coming and charge you. Then you scan the soda. Okay, the function for the soda will come and charge you. And at the end, you pay for it. So all the cashier machines are going to be functions. Any more examples in everyday life that you can think about it?
I've kind of, I guess, two questions.
Mhm.
Well, I have one question and then maybe, anyways. A function, does it necessarily have to change the original input? So like the square root, you gave it a 4, it then later on turns to 2. The original input has to be changed in order for it to be a function.
No,
Like,
no, you see, the other part is going to be operation of these are mathematical operations. The notion of the function is just when you put the 4, you get the radical 4. Radical 4 is the mathematical part that you have to do it. Okay? You know the square root function. What is the action of the square root? The action of the square root is you have to find it yourself. That give you 2. Okay, so radical 4 is just a notation of your function. It's not the result. Okay,
that makes sense.
then you have to continue with the action of the function. You see, the machine would give you $4.85. So what are you going to do? You have to pay $4.85. When you buy something. So you have to do the operations. These are going to be the value of the function, if you like. Okay, I put the 4. So that corresponding numbers. You see, 4 is related to 2. You see, that is going to be the action. So the input is 4. 4 is related to 2. Yeah, you have to simplify it. Anything else? Okay, more example in everyday life for the function.
Would an oven or a car be one?
Yeah, the car would be one. Yeah, what is in the car? Related to the car.
Oh, me, like the driver.
Yeah, you can say that, but you can relate it, for example, in the car when you drive. Okay, so your X is going to be the number of the miles, for example. So your Y would be the money that you have to pay for the gas. Okay, so that, if you want to relate them together. So the relationship would be given to the gas station is the best type of function. As soon as you go to the gas station, you see, you select, you pay, and the machine would give, that's a very good one. Because as you go with the gallons, for example, 1 gallon, 2 gallons, 3 gallons, you will see the numbers. How much are going to pay for it? That. So the gas station is a very nice one. Yeah, the cooking, somebody said, the cooking is going to be the one. Yes, it depends what you want to cook. You have to set up the number of the hours, okay, the temperature, etc. So you will find this action. You see, the function would have 2 different interpretation, if you like. It's one of them as a word is just an action that we're going to do in everyday life. But if you want to explain your action mathematically, this is how you're going to explain it mathematically. So in the case of the cars, that's it. X is the number of the miles. You can drive as much as you like, but you have to pay for it. So are going to pay for it, gas station, the function in the gas station will give you the result. So the gas station function, the pump is the best type of function that you see it. You see, it depends on which function you select. If you select the, when you want to have it, fill it up, if you like, the type 1, the type 2, and the type 3, the supreme, the regular, etc., because they bring different function to charge you. So the gas station is a very nice example of a function. Starbucks, all those fast food restaurants, or the cashiers. Cashiers machines are nice functions. Okay, any more? We have a couple of more interesting that would be useful for calculus. Let's see if you can guess. Function. In everyday life. So the driving with one of them, okay, that's it. The calculator, the cashiers, fast food restaurants, etc. The one that we love for calculus is the one that you do on April 15th. What do you do in April 15th? April 15th? You don't pay your taxes. Okay, that's one, the tax function. The tax function is the best one for calculus. You see the tax function, this is going to be tax function. It's a very good one. Why? Because for the tax function, you see, you cannot, in the history of calculus, the people think that the function must be given by one equation only. It took mathematicians many years, 50 years, to accept that the function can be defined with more, we see, more than one equation. And these type of functions are going to be called piecewise defined functions. Officially, you are going to see it, and such an important function for calculus. So the best example of those type of functions are going to be tax functions. You see the tax function or functions, this is it, the tax. You know that this is how we're going to pay your taxes. If X is going to be your income, there is a formula. It depends. If your income is going to be what, between, let's say, between $0 and, you know, just guess, it's going to be something like $30,000. You know that what you have to pay is you are going to pay 10%. So this is going to be something like 10% of your income. So we say that you are in a bracket of 10% income when you pay your taxes. But if you make more, more means if your income is going to be, let's say, you know, that's just a guess, between, let's say, $110,000, for example, then you have to pay more taxes. So your taxes are going to be in the bracket of 20%. You see, you cannot define this function with one equation because in different brackets, and you just continue, you know that. You continue if it's going to be something like more than 110,000, let's say, you know, just a guess, something like 400,000. 400, you may have to pay 25% of your income, etc. So the tax function is a very good function. So a function can be defined with more than one equation, okay? Because you are going to get in different bracket. And this function is going to be called a piecewise defined functions, okay? These are going to be called piecewise. We're going to explain it. Defined functions. They are the best for calculus. For many years, the people, they didn't use it. But there was an application in physics that forced them, you know, to get this type of functions. This type of function today is used in a statistic. Any probability function you see in the statistics, they call it distribution. So we are going to use the piecewise defined function. So the tax function. So sometimes you may have to divide your equation into different parts. You cannot use your function using only one equation. So this is called piecewise defined function. Tax functions, okay. Any question? Anything else? Like this one? Or in everyday life? So the gas station, you know, fast food restaurant, grocery stores, tax function. The other one that we love are going to be post office. When you go to post office. So I'm going to call it, you know, post office function. So what do you do in post office? You see, if you go to the post office and you want to post something, this is how much are going to pay. You know that you have to put it on the scale. On the old days, when we put it on the scale, remember they did have a booklet. they open up the booklet, say, oh, it's between, you know, if it's going to be between 0 ounce and 2 ounces, you pay whatever, 43 cents, 53 cents. And it's going to be heavier, then you have to pay more for it. So when you go to the post office, depends on the bracket. So different brackets, you different, okay, amount that you're going to pay. So you pay something like, you know, let's say you pay for the, you know, how much is it? I don't know, or 53 cents, for example, if your item is going to be between 0, let's say, and, you know, just ounces. So it's going to be heavier. Of course, you have to pay more. So for example, you know, between 3 and, let's say I go with, you know, 10, 1 pound, etc. Okay, let's say 10 pound. Then you pay something like, let's say, $3.25. Okay, that's going to be the one. And then it's going to be continue. So the post office, you see, they check it and tell you in which bracket are going to be. So the post office, again, is an example of a piecewise defined function. Okay, a piecewise defined. Okay, defined function. And they are going to be, we see it when we go on. These are our best examples. When you go to the calculus 1, when you get to calculus 3, again, they come back again. So in science, almost all the functions in science are going to be this type, the piecewise defined, because when you do a kind of experimental work, you do it in different steps. So that gives you the idea. Okay, any question? Just wanted to remind you that, you know, although we quickly go into some, you know, mathematical version of these ideas, but what we do really, we need to make sure that we can connect. In calculus, you can connect any operation that we talk about it to the function. Okay, so from our point of view for this course, a function is going to be a kind of equation, a formula between two variables, which is going to be between x and the y. But there is going to be one condition. The condition is for each x, you get only one y. So that would satisfy that equation y equal to the f of x. Okay, so that gives some idea that what we need to know. So if you want to get to any question so far, so get these examples. The functions are going to be the main tools in this course. Just make sure you have a good idea of what's going on with the function. Now, what's going to be your work, your official one, if you like, from the function that you're going to be interested in. We want to know if a function is given to you, how we're going to determine the domain of that function for us, okay? So this is going to be officially your first example. This example would be repeated in test 1, quiz 1, okay? And you're going to use it in different formats through the course. So make sure you understand it. Anything we talk about it, we are going to go through this type of function. Okay, so what we want to know, we would like to find the domain of this function for us. Find the domain, okay, of each function. This means what type of x would go through those machines. Okay, the domain. That's an excuse to introduce different functions, okay, to remind you, refresh your memory. So the first type of functions are going to be interested in this one. F of x, for example, is equal to the x cubed minus 5x squared plus 3x plus 1. You see, we want to determine the domain of the function. Let's see what does it mean. You see this x that we have over here? X is called free variables. X, you know that x is a variable, so x can stand for any number. In this course, we use real numbers only. So that's the x, free agent, all real numbers. When you drop into the function would do only these mathematical operations. So you check to see what type of operation are going to use for this function. You see the operation that we use is addition, subtraction, multiplication. You know, the powering is going to be just multiplication. So for that x, which is a number, the function would do operation with addition, subtraction, and multiplication. Just think about it. When you want to add or subtract or multiply, is there any restriction that you cannot do it? You know that we can add, subtract, or multiply any number. The only thing that's got to be careful is when you want to divide. You cannot divide by 0. If you want to take the square root, you cannot take the square root of a negative numbers. But you see the operation that you're going to use are addition, subtraction, multiplication. There is no division, there is no radical. So this means you are free. You can use any x you like, any values you like. Okay, this is the way we are going to determine the domain of the function. You just look at the operation that you have. You see to start with, your variable is free. Free means the variable can go from negative infinity to positive infinity. Okay, that's the free agent, the x. Is there any restriction? No. I can add, subtract, multiply easily. So this means this function is defined everywhere. Everywhere means from negative infinity to positive infinity. Okay, so we can say that f is defined. F is defined everywhere. Just for your information. So what's the domain of the function? And you have to write the domain in interval notation only. So the domain would be everything between negative infinity and positive infinity. So the negative infinity up to the positive infinity. That would be the domain of this function. Of course, the easier one to write it down, we accept it, or simply d is equal to the r. Set up all the real numbers. But we prepare interval notation for this course. So through this course, this is the notation I'm going to use, or this one. Any question? So that would be the domain of the function. The machine, the operation that the machine use, determine the domain. So you start with the x all the time, negative infinity, positive infinity. If there is something that restricts your operation, you have to make that restriction and change the domain. Otherwise, the domain is all real numbers. Any question? We have a special name for this function. Do you remember the name for this function?
Polynomial.
Polynomials, very good. That's the best case. So that's why we would like to introduce this one. Say that f is a polynomial. Is a polynomial just a polynomial function? A polynomial function. Make sure you remember this one from now on. So anytime we talk about it, our first example is going to be polynomials. So this is it. The conclusion is that if f is a polynomial, if f is a polynomial, then the domain is all real numbers, and be done. Use it quite a lot from now on. Any question? Can you give us another example of a polynomial?
I have a question.
Yes.
For this specific function, would there be an example of an undefined function?
No, it's polynomial.
Okay.
Not for this. Because you know that the polynomials are a combination of powers of x.
Mhm.
So the only thing that use is x squared, x to the 5th, x to the 6th, x to the 7th. So there is no restriction.
I see.
You can use your calculator and find the power of any number. That's why. So it's impossible to get it. Okay,
Yeah.
any question?
I'll tell you because
Okay, so somebody make one. Give us one polynomial. Yes, y equal to. No, radical x is not a polynomial. We just talking about the polynomials only for the time being. You see, when we say polynomials, the powers are going to be natural numbers only. Okay, so you cannot use that 1/2, 1/3, etc. Those are not going to be okay polynomials. And no, polynomials are just a combination of powers of x. We're going to see that one later on. Okay, any question for the polynomials? Make one. Give us one polynomial. So g of x equal to 1. Make one.
X squared plus 4x minus 4.
That's it. So this is a polynomial. So as soon as this is given to you, the domain is all your numbers. And we're done. Okay, our main tools are going to be polynomials. If you've been measuring business or etc., this is the only one that we talk about it. But in this course, okay, calculus 1, 2, 3, we're going to have various functions. So this is the first group. Make sure you know it. Okay, any question? That is a polynomial. So the polynomial is just using powers of x. When we say powers, the powers must be, okay, powers of the integers. Now what's going to be the second group? The second group are going to be rational function. Okay, let's start with this one. F of x equal to, okay, we get f of x equal to the, let's say, we have something like 3x plus 1. Okay, and that would be x minus 2. You can call this one 3x squared. You see, for this one, the operation that we're going to use, on the top, we have addition and multiplication, the bottom one subtraction, but we divide. You see, as soon as we divide by x, this is not a polynomial. It's a rational function. When it's a rational function, you see the solution is going to be, again, the natural domain is what? The natural domain is negative infinity and positive infinity. This is negative into positive infinity for the top and the bottom. But the operation that you have to use, you are using is division. When you divide, you must be careful. You cannot divide by 0. So you have to check, in this case, you can use any number between negative infinity and positive infinity, but you cannot use the value of x that makes the denominator equal to the 0. So check for what value of x the denominator would be 0. Any suggestion?
2.
2.
2. So we cannot use the 2. So what we have to do is we have to take the 2 out. You see, that's going to be the one. So at 2, there is going to be whole here. Okay, so what is going to be the domain of this function now? Everything except 2. The way we're going to write it down is this: domain. You start from negative infinity, you're going to the 2, union with 2 and positive infinity. You see, you have to explain it in terms of the, okay, interval notation only. Okay, so this is how we're going to, so officially, you know, that would be fine. This is the way we do it, but I just explain it. Explain that f of x is a rational function. That's the name, rational function. And is defined when x is not equal to 2. It's not equal to 2 because the denominator would be 0 for x equal to 2. So we let x minus 2 equal to the 0, and you have to pick the 2 out. So we use the open interval. Parentheses over here means we drop the 2. If you use bracket, means you like it. But we don't have it, so that's why we have to use open interval, we call it. Any question? So this is going to be our first type of the rational functions. Okay, so as soon as we see the division, that's a red flag. Okay, for the division, you cannot have the denominator equal to the 0 because that doesn't make sense. So you have to exclude the value or the values of x that make the denominator equal to the 0. So I prefer this notation. Okay, some people they use also this notation, but we don't use it in calculus. So x such that x is not equal to 2. In your book, they use this notation, but get used to this one. This is not very common in calculus. Okay, interval notation. Because later on, we are going to use it for some other concepts in calculus. And all those concepts would be explained in interval notation. And that's the case 1. There are a couple of cases of this one cases. Number 3, this function g of x equal to, so we have the x squared plus x plus 1, and over here you have x squared minus 9. Again, there is an x down the denominator, so this is going to be a rational function. So x is not a free agent. So we have to use all the, make sure that you have to avoid the values of x that make the denominator equal to the 0. Any suggestion?
3 and -3.
Excellent. So this means we are going to factor the denominator. X squared plus x plus 1. That would be x minus 3 times x plus 2. You don't have to write this, but it's good to know. So again, we have the free agent, -infinity to +infinity, but we're dividing, and there are 2 places that you have to avoid. So the places are going to be the place of a -3 and the place of the +3. So this function is defined everywhere except at -3 and +3. So the domain is -infinity to -3. Okay, 3 portion, 1, 2, 3. Union with -3 and 3. Union with 3 and +infinity. Make sure don't use bracket. Use bracket means you include those numbers and you exclude them already. Okay, any question? So that's a kind of a type 2 that we're going to have. We have another one to finish this one altogether. Any question? So the rational function is going to be your problem from now on. When you divide by x, there is one more. We don't need anything complicated, really. There are some complicated ones, but we don't need it. So the last case for the rational function for the time being is this one. Let's see what is special about this. Okay. So let's have h of x, I'm going to call it. And this is going to be x cubed plus x minus 1. But when divided by, divided by x squared plus 1. What's the special about this one? Any suggestion? The number is x squared plus 1. Okay. So infinite answers. Yes, infinite answers. You see, x squared plus 1 is not factorable. X squared minus 1, you can factor it into the x minus 1 times x plus 1. Since x squared plus 1 is not factorable, this means you will never be able, okay, to make it 0. You see, you can make it 0 if you have factors. So this means your x is free agent. Okay, so the solution is going to be, this is a -infinity to +infinity. Is there any number that make x squared plus 1 equal to 0? Never. Okay, so the domain is going to be -infinity and +infinity. You can explain it. The reason is h of x is defined everywhere. Defined everywhere. You can say that, note that, that's for your information. X squared plus 1 is not factorable. You cannot factor it. Not factorable. And so it's never 0. Again, when we ask for the domain, -infinity, +infinity is the one that we're going to be interested in. Any question? These are a various type that we're going to see And to finish this rational function, any question? No. This one is the one that you may use. You may lose something on this. Make sure that you know it. Let's see what's special about this one. So look at this one. That is, let's say that would be x squared plus 1. This is going to be x squared. Oh no, I'm sorry. I need something else. I want to give you something that's going to be a common mistakes that some people they make in calculus. And this is it. You see it quite a lot in this course. Want to make sure you don't miss it. Look at this one. What's the domain of this function? You see, x squared minus 4 is factorable. Let's factor it. See, we get x minus 2 on the top. X minus 2 times x plus 2. You see, some people, they simplify this one first. Then they find the domain, which is not correct. You see, when you simplify it, you must make sure simplification is just division. You divide by x minus 2. So just make sure that, when you divide by x minus 2, you must make sure that x minus 2 is not equal to 0. So you can do it only if you know that x is not equal to 2. So for the domain of the function, make sure you don't simplify it. Basically, this is the number line. You see? You look at the denominator. We have two factors. The denominator would be 0 at 2 and negative 2. So we have to take out the negative 2. And we have to take out the 2. So the domain, 1, 2, 3 portion. So the domain would be negative infinity to negative 2, union with negative 2 and 2. And this is going to be 2 and positive infinity. Okay. So this is going to be crucial. A couple of times in this course, this would be for some other reasons. This function would be given to you. Make sure don't simplify it. You see, if you want to simplify it, you find the domain first, and then you simplify it. So it's not going to be the case that you do simplify it first, okay? So because when you find the domain, this will tell us that the x is not equal to 2 and x is not equal to negative 2. So we can simplify it. So without domain, it's not going to be possible. Okay, so these are all the rational functions that we need. Any question? Okay, I can give you a break now because the next group of the functions are going to be a little bit more involved. We're going to talk about rational functions and the piecewise defined function. Then we finish this review. Okay, so that's going to be, you have something like up to the 10 minutes, let's say, for today. Okay, it's a 9:20, 21. We come back at 9:30 and we give you the rational functions. Okay, see you there.
Hello? Hello?
Yes, question.
Can you please slide, move the paper, go to the very first one. No,
First
like,
page.
yeah, first page. Yeah, thanks.
That's it. That's the first one.
Okay, thank you. I just wanted to review it real quick.
Oh, okay. There. Okay, so see you in 10 minutes. Okay, so we are going to continue getting to the next group of functions. It's going to be very important functions. Okay, so we talk about the rational functions, polynomials. Now, the next groups are going to be radical functions. Okay, so we continue with the number 6. Let's put the number 6 here. Okay, for the radical function, we are going to have a group of different groups. So let's start with this one. And the function is f of x equal to, say, the square root of 2x minus 1. You know that anytime we have a radical function, we got to be careful. And when you get the root of the numbers, if you take the odd root, the 5th root, you know, the 3rd root, the 7th root, etc., we can do it for any numbers. But when we get to the square root or the even root, the 4th, the 6th, and in calculus, since we're using only real numbers, you got to be careful. You know that we can find the square root of a non-negative numbers only. So if this type of function is given to you, that's a radical function. So what we are going to do is we look at the index of the radical. Index is this. When there is no number, this is the square root function. So the index is 2. If there is going to be anything else, they put the numbers here for you. So you check the index. If the index is going to be even, you are in trouble. This means you cannot use x is not going to be a free agent. You have to make the x so that this expression is never negative. Okay, so the solution is going to be, we look at the index first. We say that the index of the radical, okay, index is equal to 2 is even. When it's even, there is a question mark, means you have to work. So the work is going to be f is defined. You know, you can do this one right away. I just explain it. F is defined when or where 2x minus 1 is greater than or equal to the 0. So that would be the restriction that you have. Okay, now you have to solve this inequality. 2x minus 1 greater than or equal to 1. So that gives you a 2x greater than or equal to 1. So x would be greater than or equal to the 1/2. So function would be defined when x is greater than or equal to the 1/2. But you have to write down interval notation. You see 1/2 greater than 1/2. 1/2 up. 1/2 up would be, the domain would be 1/2 up to the positive infinity. Or the positive infinity, we use parentheses because we don't have the positive infinity. But for 1/2, since there is equality sign, we're going to use a bracket. So that would be, okay, so that would be the domain of your function. You see, this is going to be the number line that you did have. That was a negative infinity and positive infinity. So you have the 1/2 here, and the 1/2 is included. So that's going to be a solid point, 1/2 up. So up. So this means this is going to be the domain of your function. Any question? So for the radical function, you look at the index of the radical. If the index is going to be odd, nothing to worry about. You can have any number inside. I'm going to give you an example in a minute. But most of the time, the index is even. When it's even, you have work to do. What are going to do is going to be even number. So 2x minus 1, you set it up to be greater than or equal to the 0. Then you have to solve for x. That's easy to solve. You get x to be greater than or equal to the 1/2. So the domain would be 1/2 up. So 1/2 and positive infinity. Okay, that's the case 1. Any question? Now what will happen if the index is going to be odd? That would be our easy case. Okay, so that would be number 7. Most of the time, this function would be given to in calculus because they want to make the domain easy domain. F of x equal to This is the function that we're going to use in future. The fifth root of x squared minus x plus 1. You see the index is odd. When it's odd, it's free. You can have the, you can have the fifth root of positive numbers, negative numbers, or 0. You see the fifth root of 0, for example, is 0. The fifth root of positive 32 is just 32, is 2. The fifth root of negative 32 is negative 2. So we have nothing to worry about. So you forget about the radical. What is inside is the polynomial. And the polynomial is going to be defined everywhere. So simply the solution of this one is going to be the index 5 is odd. Forget it. Forget about the radical. What is inside the radical? The polynomials. So we can say it's odd, and domain of the function is going to be all real numbers. Easy case. Any question? So you have to check the index of the radical. If the index is odd, you can take the fifth root of any number you like. If you use calculator and find it. But it's going to be, if the index is even, you cannot use the negative numbers. So you have to exclude those numbers. Okay, any question? Now, there is one tricky one that we're going to use in this course. So make sure you know this. There's a couple of algebra or algebraic expression involved. I want to check it. Let's see how we're going to handle it. So let's have the g of x equal to, let's have the fourth root of the x squared minus 9. We want to find the domain of this function. Look at the index. 4. 4 is even. When it's even, this means you make sure that this is not going to be negative. Because the fourth root of a negative number is not divided. Remember, no complex numbers. So this is how we're going to handle this one. Solution. Index of the radical. 4 is even. So you put the question mark here. So what's question mark? This means G is defined. Again, you can do it right away. I explain it. G or G of X is going to be defined. Defined, then X squared minus 9 is going to be greater than or equal to 0. Okay, X squared minus 9 greater than or equal to 0. So you have to solve this inequality. And this is the one that, sometimes we have a difficulty. Okay, any suggestion? How are we going to solve this one?
Move the 9 over and take the square root.
Very good. 9 over, taking the square root. Okay, what's next? What's the radical x squared?
X.
Okay. Any other suggestion? What's the radical 9?
3.
Okay, this is correct. Radical 9 is 3. But radical x squared is not x. Okay? Because you see the output of the square root must be a positive numbers all the time. So when it's the radical 9, you say it's 3. That's fine because 3 is positive number. But when you say x, what is x? Remember, x is a free agent. X can be positive or x can be negative. So how are we going to guarantee that this result is positive? This is used quite a lot in this course, and that was an excuse. So you note that in this course, when you take the square root, you see the radical x squared is always absolute value of x. Okay, you put the absolute value of x. If you have extra information that x is positive, you call it x. If you have information that x is negative, you call it negative x, okay? So radical x squared is absolute value of x. So this means this would be absolute value of x greater than or equal to 3. Okay, any question? You're going to use it in the notion of the limits later on, limit that by infinity, positive infinity, infinity, and some other parts of the calculus. So in algebra, when you say x, because you assume that x, for example, is positive, okay, and sometimes they say we take 2 square root positive or negative. Some people, they say radical x squared is positive negative x, which is very bad. The answer must be a unique answer, one answer, and positive. So put the absolute value all the time. Okay, now the absolute value of x is greater than or equal to 3. You have to find this one. You know, the different way to do it, the best way, absolute value is your distance from the origin. We call it your distance from your home. You see, this is the way you can find it. So this is home, the origin, 0. For the absolute value inequality from algebra, you see your positive 3 here. And this is going to be a negative 3. When the absolute value is greater than 3, since means you are 3 miles from your home, if you like. You see, bigger than 3. This is 3, so greater than 3 is here. And since the absolute value is like looking into the mirror, or you may be here. See? Absolute. If it's going to be less than 3, you are going to be between negative 3 and 3. If it's greater than, far to the right, okay, and to the left. And you say my distance from my home is bigger than 3 miles, means you are not going home. You are far from your home, okay? So this is going to be the domain of the function. Domain of the function is going to be 2 portions, 1 and 2. So it's going to be from negative infinity to negative 3 bracket, union with bracket 3 and positive infinity. So that gives you the domain of the function. Any question? So we're going to use this one in several places in this course, okay? And we do it without explanation when we get to that part. So again, this difficulty arises when the index is even, of course. If it is 5 or 7, nothing to worry about. In that case, that function is defined everywhere. But when it's an even number, you have a condition. The condition is x squared minus 9 cannot be negative, so must be greater than or equal to 0. But then you have to solve this inequality. So just moving to the other side, take the square root, but make sure you apply the fact that the radical x squared is the absolute value of x. Now, absolute value of x is greater than 3 means x is greater than 3, if you like, greater than 3. Since it's an absolute value, it's symmetric, or the other side, looking into the mirror. So that gives you the domain of the function. Of course, you know, if you don't like this method, some people apply this method, but I prefer the first one. But if you do it on the test, we accept it. It's just algebra, you know, in algebra, if you want to solve x squared minus 9 greater than or equal to 0, you know, that use factoring. It's x minus 3 times x plus 3 greater than or equal to 0. You let it equal to 0, you find some numbers, you call it in algebra boundary numbers or critical numbers. X would be negative 3 and x would be 3. Then what you do in algebra, you get the number line, negative infinity to positive infinity. You put these numbers, this is going to be a negative 3, and this is going to be a positive 3. Then you have to drop some numbers, checking some numbers to what's going to be the sign of these regions. For example, you pick something like negative 4 here, and you drop it into this equation. So that gives you 16 minus 9, which is positive. 7 is positive, so we say this is positive. And in this region, you pick another number like 0, and you put it in this, so that gives you 0 minus 9, which is a negative. So this would be negative. And over here, you pick a number like a +4, and you drop it here, that gives you 16 minus 9. It's a +7. Okay, you are interested in positive. So we're going to shade the positive part. That give you the same answer. So the domain of the function is the shaded area. It's a -infinity to -3, union with 3 and +infinity. We need both methods for future in this course. There are some places, especially at the end of the course, when we get to the exponential function, rational function, we use this type of ideas of testing the numbers. It's just an excuse. I want to remind you that we are going to use this inequalities in future. Okay, just pick the method that you, for this function, I use the first method. But later on, I use this sampling, this checking one for the trigonometric function, not now. For the trig function, sine, cosine, tangent, secant. So remind yourself that there is a, we call it testing, test numbers, if you like, to get this result. Okay, any question? So that's your challenge, challenging one, that you got to be careful about it. You will see the couple of places when they want to give you something a little bit more involved. This is going to be the one. This would be given in 2 different versions. I give you another one. If you switch this number, these 2 terms, so the domain would be a little bit different. Any question? So pick the method that you feel comfortable to be able to do this one, and make sure you know both methods for future application in this course. Okay, so let me switch it so that you can see the difference. So this is one of your question on your first quiz. Later on, we are going to have different notion. We got the notion of the continuity, differentiability. When you study those, when you come back to these functions. So if you get these functions and make sure you understand it, how you operate it, especially finding the domain would be very useful for you. Okay, so let's see what's the difference if they switch it. Okay, I just use different notation, so we get to know it. I use this notation. How about the 1 minus x squared to the 1/2? Sometimes they use a rational equation. You know that we change this one to the radical. Okay, so the solution is going to be, just a reminder, these formulas that we're going to use. Note that. Make sure to remember these formulas from algebra. If you have x to the 1n, this is going to be n root of x. Okay, this is how you change the rational power into the radical function. And in general, if you have x to the m over n, this is going to be the n root of the x to the m. So we use these formulas quite a lot in this course. Just make a note for future application. Okay, x to the 1 over n is going to be n root of x. X to the m over n. You see this, the denominator is always going to be the index of the radical. Okay, again, these are, make a record of these formulas that we're going to use it. So change the function. So your g of x is going to be equal to, get the square root of 1 minus x squared. Okay, we change it to the radical function. So the index of the radical is a square root, so index is 2, so we are in trouble. Okay, index is 2, 2 is even. So we have a question mark to answer. The question mark is going to be g of x is going to be defined. It's going to be defined, of course, if 1 minus x squared is greater than or equal to the 0. Again, you have to solve this inequality. You can use factoring method that we talk about it, or the square root method. So I'm going to keep the negative x squared. I move the 1 to the other side. I have an extra job. This is the negative. I want to multiply both sides by a negative number. You know that if you multiply by a negative number, you have to reverse the sign of the inequalities. Okay, so what I do, I'm going to multiply both sides by -1. I just explain it. So I have a -1 times negative x squared. So since I multiply by negative number, I have to switch the signs of the inequality, direction of the inequality. Okay, so it's going to be -1 times it by -1. Just make sure to remember, when you multiply by negative number, you switch. So now that gives you x squared less than or equal to 1. Any question? Just to remind you, because we're going to use it in future. Now we continue with the square root method. It's a radical x squared less than or equal to the radical 1. As we talk about the radical x squared is the absolute value of x. Okay, less than or equal to 1. And so in this case, you get your number line. It's a negative infinity, positive infinity. Your distance from your home is less than 1 mile. For example, this means you're going home. You see, you get the home origin, 1 to the right, a positive 1. It's absolute value, so 1 to the left and -1. Okay. So where are you? X less than 1, less than 1. Less than 1, you go inside. You see, less. When it's greater than, you go outside. Less, this is less. So your domain is going to be everything between -1 and 1. So the domain of the function is closed interval of a -1 and +1. That is the domain of the function. You see, compare them together, make sure you don't miss it. In the other one, that was the direction was different. You see, if it was absolute value of x greater than 1, so you pick the complement, okay? The portion to the right and the portion to the left. When it's a less, you see x less than, less inside, greater than outside. Okay, so the domain would be two different things. Over here, so look at this one. The domain is two portions because you are outside. But for the other one, the domain is going to be one portion, and that would be inside. Okay, any question?
Yeah, quick
Yes.
question. So you moved over the 1. Would
Yes.
moving over the negative x squared not be a good way to do it?
Yeah, you can do it.
Okay.
Yeah. The other option is, you see, the other option is going to be, yeah, I just want to go through this just to explain when we get these negative numbers. That's the reason that I did it. But this is it. So you can move the x squared to the other side. So that gives you 1 greater than or equal to the x squared. Okay, which is the same as x squared less than or equal to 1 when you read it from the other angle. And then you continue. That gives you the 1. Okay, it's the same thing, but yes, you can do that. And of course, this is going to be negative infinity, positive infinity. And we have the home and a positive 1 and the -1, so we get the same thing. Yeah, I just want to go through that method to explain it, to remind you. Very good. Any question? So your challenge is going to be number 7, 8, and 9. You get these quite a lot in different places through the course. Just make sure you remember it. And you already got your practice quiz number 1 is already posted. If you check it, you see the function similar. Of course, the way we use it in calculus is When we give you this one, we have a notion of continuity by the end of this week, which is the same thing. Then we ask you find the intervals where the function is continuous. It's the same thing. You just find the domain for us. So we are going to be ahead when we get to that point. Okay, so these are going to be there are a couple of more functions, exponential function and the natural log function. The way you do it, the textbook that we use in your college, they talk about that 2 functions would be given to you through the end of the course, chapter 5. So that's why you are not going to see any example of the exponential one and the natural log function unless we get to the chapter 5. It makes things easier for you, but I don't like it because we have to wait to get to that function part, but it's okay. Some people, they say, if you want to calculus 2 would involve with those 2 functions, that would be more useful. So don't expect any of those type of function for the next 3 weeks. So these are our tools. We get, of course, the trigonometric function, which is the domain is clear. All of them are going to be defined on the natural domains. Okay, so we have one more important group that we have to talk about that one to finish our review. And these are the ones that we're going to use quite a lot. And you may have seen it, or of course you've seen it in your pre-calculus class, but not the way we like it. Okay, this is it. So remember we talk about I have one more example. I'll give you this one because I don't want you to be surprised. Okay, let's give you one more. Just be expected. Don't expect these numbers to be nice all the time. Okay, so I'll give you this one. It's good to have this. Some people would be confused. Okay, how about this one? Okay, having something like 3 minus x squared. But just to show you that it's not always nice, perfect squares. Don't worry. So we can do this one quickly. This is the way we do it. Solution. Again, it's a radical function. Index is 4. So the index 4 is even. So we have work to do. So the work is you set 3 minus x squared to be greater than or equal to 0. You have to solve for x squared, whatever method you like. I use my method. I just leave this one as is. So I multiply by -1 quickly. Remind myself that I have to switch. Okay. Now when we take the square root, this is what I mean. So we get a radical 3. Don't use any decimal number, anything. A radical 3 is nice. It's a radical 3. For domain of function, we don't use calculator to say that it's a 1.7. If it's going to be application problems in future, yes, but not for the domain. You keep it as is, but the radical x squared is always absolute value of x. So we get absolute value of x to be less than or equal to the radical 3. Now we know it. Number 9, negative infinity to positive infinity, home. So this is home. Radical 3 to the right, radical 3 to the left, negative radical 3 is less. Less go in. That's it. If it's greater than, to the right, to the left. So the domain is going to be simply from negative radical 3 to the positive radical 3. And you do that. Okay, so don't be surprised. This is nice. This is the final answer. Okay, don't change it. So we have a couple of cases that we get, irrational solutions. Any question? So let's get on to that very important and the last group. Several places we are going to use this one. Quickly, we use it in quiz 1. Remember, we talk about tax function. We talk about the post office. This is a situation that your function is not going to be given by one equation. You may get 2 or more than 2 equations. This function is going to be called piecewise different. Okay, so they are very important. So let's revisit it. and to see the way we like it in calculus, not pre-calculus. So what's a piecewise defined function? Okay, that would be a piecewise defined function. So it's going to be a function that's defined by more than one equation. Okay, let's remind you what we mean by the piecewise defined function. So a function okay, a function f that is defined, that is going to be defined by several equations. Is usually, you know, 2 or 3, several equations. On, of course, its domain. We partition the domain, different parts, and, you know, different formulas. By several equation on its domain is going to be called a piecewise defined function. Okay, a piecewise defined function. That's it. Okay, like a post office function, tax functions, or most of the, you know, all the functions in when used in probability, various form, different brackets, different formulas. So I'll give you an example to see how you all work with these functions. And at this level, we are going to be interested in the graph of these functions. Okay, let's give you one. Suppose this is going to be your function. F of x is equal to, you see it's a 2x minus 1 when x is less than 1. And that would be x squared minus 3x when x is greater than or equal to 1. You see this function is partitioned at 1. We divide it in 2 parts. Okay, so if you want to think about it, the situation we're going to have is this one. You see, this is the natural domain, negative infinity to positive infinity. So what we did, we partitioned it at 1. So this is going to be 1. Now, when your function, when x is less than 1, the function we use this formula. So the machine reduce y equal to the 2x minus 1. But when x is greater than 1, the function would use this formula, y equal to the x squared minus 3x. Okay, so as you can see, the domain of this function is negative infinity, positive infinity. When you want to find the domain of the piecewise defined function, just check to see what will happen to the partition point. If equality is given to you, this means it's defined everywhere. But if the equality is missing, this function is defined everywhere except at 1, for example. So in this case, f is a piecewise defined function. F is a, okay, that's it, piecewise defined function. Of course, with the domain of the all real numbers. Any question? So let's see how this function would operate if you want to find the value of the function. So when you give the x to the machine would check to see if that x is coming from the first part or coming from the second part. If it's coming from the first part, the machine use 2x minus 1. If it's coming from the second part, that give you x squared minus 3x. So for example, note that. Suppose you want to find f of 0. So you check to see where is f of 0. Is it in the first portion or is it going to be in the second portion? 0 is less than 1, so 0 is here. So the function would use this formula to find it for you. So the function use 2 times 0 minus 1. Okay, so that gives you 0 minus 1, which is going to be a negative 1. So f of 0 is equal to negative 1. Remember, you cannot use this both parts, because remember, for each x, you get only one y out. So you identify where the position of the x is to using the proper formula. Any question? Suppose you want to find f of 1. 1 is a partition point. You check to see where the equality is given to you. You don't have x equal to 1 here, so you are not going to use the first part. There is equality sign here, so we use the second part. There is going to be a case that the equality would be missing from the first and the second part. If it's missing for both of them, so f of 1 is undefined. Okay, in this case, we can do it. So we're using the second part. Okay, so that gives 1 squared minus 3 times 1, which is going to be 1 minus 3, which is going to be negative 3. So f of 1 is going to be negative 3. And you're going to use it when we get to the first section of the course. Any question? So if this is missing as well, remember, f of 1 is undefined.
Isn't it supposed to be
Negative 2,
negative?
negative 2, negative 2. Yes, thank
Yeah.
you. Negative 2, thank you. Negative 2. Okay, so f of, thanks, f of 1 is going to be negative 2. Thank you. Any question? How about, for example, how about f of pi? Which part are you going to use for this one? The first part or the second part?
The second.
The second, very good. You know, pi is 3.14. So we're using the second part. The pi is here. So the result is going to be pi squared minus 3 pi. Okay, then you can use your calculator to find it. So be prepared for it, to understand it and how we're going to operate with this type of functions. Any question? So knowing it is important for us because we're going to use it quite a lot. These are the best examples, unusual example for calculus. And when we get to the future application in science we use only piecewise defined function. So, you know, that's why you any topics that we talk about it, we are going to throw one of these examples out or in so that you practice to get these numbers. Okay, what's going to be your challenge so far? Your challenge is going to be how going to graph it for us. Some easy graph, because we use graph sometimes to explain the topics. And we are going to have some disagreement, if you like, on this graph for the first quiz and the test. So I want to give you the instruction that how we are going to use it in this course. Okay, so that's an important part of these examples. So there you are. And you will see both of them in your first test, first quiz. You get one question on this one from the function. Okay, let's say how we're going to sketch these graphs, okay, in calculus. We want to sketch the graph of each function. The graph of each function. There are two types. I'm going to do one of them today, and I finish the second one probably tomorrow. Okay, let's see. You see this, to see it, for the time being, we cannot give you anything complicated because we don't have the tools. So it's going to be just just a straight line. Most of the time, if it's going to be curvilinear, it's very easy one. So the function is this: 2x minus 1, x is less than 1. We have x plus 5 when x is greater than or equal to the negative 1. You see, you want to graph this. You see, it's a two portion. So the graphing is going to be the same thing. You are going to graph the first part and the second part. And of course, you are going to graph them using only one XY coordinates. Okay, and then you may be able to connect the first and the second together, or you may get two disjoint pieces. Later on, if you connect them together, we say it's a continuous case. And if you cannot connect it together, we say discontinuous in future, but not now. Now, let's see how we're going to do it. Remind ourselves that it's a two portion. You don't have to write this, but I just explain. So we are partitioning it at -1. Remind ourselves that's going to be -1 that you got it here. So if you stay with the first part, the function is y equal to the 2x minus 1. If you stay with the second part, the function is x plus 5. Okay, believe this function done and graph it. So we're going to graph y equal to the 2x minus 1. You know that you have to identify some points and optional points to get it. But there is a restriction here. Anything you pick for the first part, so x must be less than -1. So make sure you pick the numbers that are going to be less than -1. So I get this T chart. This is my x, and this is my y, which is going to be 2x minus 1. Restriction is -1, so you have to pick -1 down. -1 always. We start with the -1 down. Down something less than -1, like a -2, -3, etc. But you must start with the -1, okay, because of the limits. You have to make sure you're not going to go over it. Okay, so -1 done. You go back and substitute. If you put the -1 here, so that give you 2 times the -1 minus 1, that give you negative. Okay, so that was a 2x. So that give you -1 minus -2 minus -1, -3. And if you put the -2 here, so that give you 2 times the -2 minus 1, which is going to be -5. Okay, get the xy coordinates. This is going to be xy coordinates. And graph the first part. So what do we have? We have a -1 and -3. -1, -3. 1, 2, 3. -3. Okay, so it's going to be -1 and -3. This is the first point. This is kind of your limit, x less than -1. But you have to check to see if this partition point is covered or not. You say x is not equal to. When it's not equal to means this point is not going to be on the graph of your function. So you make a hole here. Okay, so if this is going to be equal to, you make a solid point here. That's why it's not important really. Some people, they say you can't take the -1 because there is no equality sign. The situation is you have to estimate it. So we pick the -1. If we don't have it, we take it out. It's like you invite somebody to come. This is his or her chair. She's not here or he's not here. So we make a hole. But you have to start with the -1. Okay, the next point is a -2 and -5. -2. -5. That was a -3, 4, 5. So that give you the second point. And you know, there's less than -1 means you go to the left only. So you pick this point and you go to the left forever. This is going to be the graph of the first part. Any question? So that's why you get the -1. So just make sure you're not going to go over it. Okay, forget about some people, they say, oh, I like to use intercepts. No, since there is a restriction here, you have to get the restriction first, -1, to make sure you're not going to go over it. You pick -1 done, -1, -2. When you graph it, you start with the -1, -3. If there is equality sign, you make it solid. Okay, if the equality sign is missing, so you don't have this point, you make a hole. Then the next point, you go to the left only. You cannot go to the right, because the right means x is greater than -1. That's why we must start with the -1 to make sure we are on the right place. Any question? So if you do anything else, your graph is wrong, and you won't get any point for it on the test. Okay, so that's going to be the first portion. We have the second portion. Okay, then -1. So let's start with the second one. So the second one, y equal to the x plus 5. Okay, with the restriction that x is greater than or equal to the -1. Same thing. Get this xy coordinates or t-charts. So that would be your x. And that would be your y, x plus 5. Again, you start with the restriction, -1, up, up, something bigger than -1. Give us a number. Number bigger than -1, but close to -1.
0.
0, excellent, that's it, 0. So go and find it, substitute. So that give you -1 plus 5, which is going to be 4. That gives you 0 plus 5, that gives us 5. Okay, go back to the same xy coordinate and get the second part. That's it. You get back to the -1 again, -1. -1 and 4 this time. -1, 4, 1, 2, 3, 4. You see, this is going to be -1 and 4. Now, do you have it? You check. There is equality sign. Since equality sign this time, this point is part of your graph. You see, that's a solid because you get one here, but this is not a solid point. You know that you cannot have two solid points over here. Remember from your previous course, vertical line test, a graph represents a function if each vertical line intersects the graph at one point only. So if you have two solid points here, so this means you're intersecting the graph at 2 points, which is not correct. So that's why. If, of course, this was missing, you make a hole here again. Okay, so we have it here. Now, -1, 4, then 0, 5, 0, 5. That's a 0, 5. That was 4, 5. So it's going to be another point. You connect and you go to the right this time. Up, up, up. That's it. This is going to be the graph of your function. Very nice graph, and we're going to use it to analyze various things later on. So you see this is nicely represented. X less than -1, use this portion. If you want to do anything with the x greater than -1, use that portion. And this is the one that we are going to use it at the next section to define the limit of the function. If you want to find f of -1, you check the f of -1. It's not here. It's here. So f of -1, this is the 4. And this is going to be the 5. Okay, especially this portion, you have to just refresh your memory regarding this part, which is going to be very, very important. Okay, to give you this one. Okay, any question? I have one more example to give you. I write it down for you. Let's see if I can do it today, but otherwise I finish it tomorrow. This example is from your book. It's very tricky example. And we use it a couple of places in the course. Okay, so I just write it down. All of them are just a straight line, but this one is a little bit tricky, curvilinear, but not bad. So the function is x when x is less than 0. Okay, it's 2 when x is equal to the 0. Okay, and this is going to be x squared when x is greater than z. That's a very popular example for calculus. That's why we want to make a note and then you keep it for future. Okay, I'm going to do it tomorrow because this is the first day. I have to get to my next class. So you just think about it. Then we finish this one tomorrow, and that would be our the final part of our review. Okay, any question? So study this carefully, because from now on, these are the tools that we are going to use it for the next something like 3 weeks. Anytime we need a function, we bring this group up. So refresh your memory. Okay, if you don't need more problems really, but make sure you know it. So what we're going to do today, tomorrow is we just studying officially what is going to be calculus about. Okay. So I will post. I have another class up to the 1:30. Then I'll check the Zoom. The recording would be ready by that time. So I post the recording and I make a scan my lecture notes and I post it for you in case you missed it. Okay. So when you come back tomorrow, make sure you know everything about the functions. And if you have any questions, okay, we can talk about it. Okay, that's it. Any question? So check
No,
the
thank you,
syllabus,
Professor.
especially, thank you, especially for those things about the, okay, checking the what's that, APC, make those arrangements, make sure you're not going to miss anything. And again, if you need anything, send me an email and we can meet on Zoom 5 to 6. Okay, take care and have a good day. Bye-bye.
Thank you. Have a good day.